Okay. Can everybody hear me? Anybody hear me? Hello out there, Etherland.
I hear you.
Okay. Um, we're currently in the topic of root locus. Um, you'll find that I did post some problems that have been used in the past, homework type, and I'm not sure what else to say. Um, we really didn't get very far in the subject yet, so I'm not sure you have any questions. Um, other than the fact that the topic has a lot of dimensions to it, so that's why it gets its own chapter. Um, so I'm going to kind of do a short brushstroke review where we are, where we left off. I think we're only at the beginning of the notes anyway. Let me see. Uh, Stop me if you got a question. The figure here is the starting figure for the chapter. I tried to convey the idea that it's not the only relevant figure, as we'll find out. We can, in fact, include a transfer function, feedback in the feedback loop. We can have a transfer function, non-unity gain. And so, you know, the transfer function for the unity gain could be jazzed up, and later on, still relevant. Many of the ideas, essentially all of them, we'll go over. However, in the beginning, we take a simple case. So it's really just, that's all it is. Just to get an idea of what the root locus is about. Anyway, so I think we established we can come up with a transfer function from the canonical form. We can get the characteristic polynomial, and then the characteristic equation is obtained by setting it to 0. We see that this is so-called root locus parameter that appears multiplying the g of s in that equation. And an important point that is an element that leads to two of the rules for root locus is that if you take a look at this basic formula in this form, actually for root locus purposes, it's often rewritten in a very sort of simple modification, but an important one for our purposes, by taking the 1 to the other side. And we see we get a minus 1 over there. So from that, we can see that there's a condition placed on the magnitude of the k times g, which is that has to be real and positive, but in this case will be 1 for that because of 4. And the second is that the angle associated with the complex quantity would be, since it's a -1, would be 180 plus multiples of 360, which of course brings you back to the negative real axis. So those two will come up again and again, as we'll see. So let's go to the next page. I think we did start on it, possibly. Yeah, I mentioned to you that the root locus is really not unique to the transfer function. Many different transfer functions can have the same root locus. Might be worth bearing in mind that pretty much the root locus is based on the denominator, and you could say, well, transfer functions have both a numerator and denominator, so it's quite reasonable from that viewpoint to say, well, you could have different transfer functions which would have essentially the same root locus. And to make that case clear, we saw on the previous page this block diagram, which is the one used in the book. And I will point out to you that, in fact, this one also gives you the same denominator as this one did. And therefore, this one would also give us the same root locus, even though they're different transfer functions. Any questions so far? All right. So we're gonna continue with the version of the block diagram that the book has. And for when I say the book, in this example, we're going to take a specific example where our G of S has a pole at 0 and then a pole at a -2. And here's our essentially our transfer function, which we can explicitly, by substituting in the G, get the intermediate form. With a little bit of simplification, we can write this as a polynomial, quadratic type, in the denominator. And so we would argue that our characteristic equation, after setting the characteristic polynomial to 0, would look like that. And surprise, surprise, we can use the quadratic formula since it is a quadratic. And when we do, the only real parameter in this thing that potentially can vary is, of course, the root locus parameter k. So I'll let you confirm, all of your experts at quadratic formulas, so I'll let you confirm that after simplification you get the result that we see, -1 plus or minus the square root of 1 minus k. All right. Now we're going to look at it pretty much the way we often look at it, from the viewpoint that k is greater than or equal to 0. So we'll start off by taking the first value of k we'll look at will then therefore be 0. So if we take k equal to 0, by just plugging it in to our roots, we see that we have two distinct roots, one at a -2 and the other one at 0, right? Because if you put k equals 0, you get a -1 minus 1, which gives the -2, or you get a -1 plus 1, which gives you the 0. So now we see, well, this root locus, as far as starting on where the poles are at, where the poles are for k equal to 0, would be those two values. And so, yeah, I show that's one of them there and the other one there. That's for k equal to 0. Okay, so repeating I think we had on the previous page. Repeating our general result here for the quadratic formula in terms of k for reference purposes, which we saw came out to be that. We then can look at it and say, well, we can see what is happening between the values k equal to 0 and k equal to 1, because there's no place in there that this is negative. Therefore, the quantity has to be real all the way. So the roots are going to be on the real axis, we would say, that's for sure. And we can see that as the k became bigger between 0 and 1, even including 1, we see that in fact the two roots actually would they both remain real. This term becomes smaller. So the fact is, eventually you get to a point where both roots are sitting right on at k equal to 1 are sitting on the same value of a minus 1. And of course, it's repeated at that point. So between k equals 0 and k equal to 1, we can visualize. Here's a visualization if you want that. There's the original pole for k equals 0 at 0 and a minus 2, and they, as soon as the k starts increasing, both poles start moving in the direction towards this vertical dash line where it crosses the real axis at a minus 1. And then we could argue that it ends on, at least this part of the story, ends where k is equal to 1, where you have repeated roots, and both those poles are now sitting at the value of a minus 1 on the real axis. If I'm going too fast, say so. If you got a question, ask. Okay, so you can see what's happening here. Then the next step is we're going to consider k greater than or equal to 1, in which case we have this consideration. We have to give this square root, because once k becomes bigger than 1, we're taking the square root of a negative number, which is okay as long as we handle it correctly. So I would argue you can write the 1 minus k as a minus k minus 1, just from algebra viewpoint. And since the k is, let's say, bigger, as long as k is greater than or equal to 1, that part in the parentheses, k minus 1, will never be negative, but the minus is still up front. So what we can do is square root of a times b is square root of a times square root of b, and use that here and remind ourselves square root of minus 1 is j. That's where it comes from. And then we could say, well, in the domain we're interested in, you could say where k is greater than or equal to 1, we can say our roots would look like this, which is the smoking gun for having complex roots. That's not an accident there. And we would argue then as k becomes bigger, then what happens is the real part doesn't depend on k, and the minus 1 part right there doesn't depend on k. So then the second part does, and that's the part that moves it up and down along. Essentially, its imaginary part then increases as k gets bigger than 1. And so what happens is the roots, the poles in this case, the poles for the problem, which is the roots to the characteristic equation, they move in opposite directions along the vertical axis, along a vertical line, which crosses at a minus 1. And the argument would be as k gets bigger, they continue to move farther and farther away. Since it's plus and minus, we see the plus 1 would be on the positive side, the minus would be on the negative side, but they're symmetrically located with respect to the real axis. Any questions on that? Any questions?
No.
No. Okay. You can see that indicated on here, there's this angle theta. We'll see the implication of that. You may not be surprised to know that it's the same theta we had before for our second order systems. But we're going to do that more carefully on the next page. But you could argue right now, what we have done is pretty much generated our first root locus. I mean, you could argue that if the objective was only to produce the root locus, that we would be, essentially, we've done it. Okay. Now, a little bit of the next part of the story kind of ties back to, well, one of those applications is sometimes you can use the root locus to put limits on certain quantities that you do not want to exceed some value, like a percent overshoot, as we'll demonstrate. So that's kind of where we're going here with this. So we're not quite done with this. You could argue we got our root locus, not using any root locus techniques, by the way, just by just using the mathematics that goes with solving equations. We'll see later that the example has elements you can pull out that will connect to the techniques we need to know. But right now, that's all I would say is we haven't used the root locus techniques, but we have used the math, and that would be the root locus. And I think the reason why the math worked out so nicely here for us is because relatively simple problem. If you made it a lot more complicated, it would have been not so simple. And that's where kind of like the root locus wins the foot race over just straight away solving problem and solving for the which we did pretty much solve for the roots of the characteristic equation. Okay, so let's go on. I mean, like I said, I refer to this data here. So let's see what happens. All right, so I'm going to remind you that when we were doing our second order analysis, we came up with the general form for that second order system in terms of a natural frequency and a damping ratio in terms of S look like this. Okay, now what I need to do in mind, let's do this. Let's might be good. All right. We did that page right. Okay, now let's see if I can use the magnifier here. How do I get rid of this? Okay, anyway, let's see if we can all right. So there is our standard form for a second order system, which we can, setting it to 0 gives us the characteristic equation. And as we might have, if we made notes on it, we would see that the problem we just solved also had a quadratic, and it took the following form. Now, there is a figure that which is in the notes, which is in the text, also in the notes. And I want to make, I think, an important point, which could be overlooked if you just saw the equation on the figure. So we're going to make an issue of that, clarifying that. So let's just say instead of the one we have here, I'll use this arbitrary gamma here. And we say for the specific problem, this gamma is equal to 2, which we would hopefully agree. All I did was replace that with a symbol, which I could put in some other number if I wanted to later, but let's just say that's what I have. We can see that we can make the root locus constant. We would need to make the root locus constant equal to the omega n squared for consistency of these two forms, which is usually done. So that gives us a connection between the natural frequency and the root locus constant directly, square root relation. We would also argue that in comparing this one with this one, the coefficient of the S, first order S, would be the same as the gamma. So we could say, okay, if we then set those equal and solve for the damping ratio, it would be this. And solving, let's see, and then putting in for the natural frequency, the square root of K would give us this one. And even though it was just a slight detour, now we can go ahead and set the gamma to 2. And if we set the gamma equal to 2, we see that the product of the damping ratio natural frequency is equal to 1, right? Okay, so you'd say, well, if you set that equal to 2, then that 2 cancels, and that's got to be equal to 1. So then as a byproduct, since our, if you solve for the damping ratio here, you get 1 over the natural frequency, but the natural frequency is the square root of k, so you get this form. Speak up if I'm going too fast, or any question about that logic. Okay, now I will remind you that we did it before, but I'm not sure it's right off the top of your head in terms of memory. So I essentially reset up again the roots for the second order quadratic form right here. That's negative b plus or minus square root of b squared minus 4ac over 2a. A is equal to 1, so it's only 2. And whoops, what happened there? Let's go back. I know what happened. All right, so now if you simplify this a little bit, because you got a lot of 2's running around, easy to do that. This would be the equivalent form. Now, we can take a look at this and see that what we have here is we essentially have this almost essentially the same problem as before, but just in different terms. In the sense, let's just do a quick few steps. We see if we recognize that this result will be correct, okay, throughout. We can just go ahead and replace that with a 1 there, and replace that with k. And I'll let you check that's exactly what we came up with just for brute force mathematics on solving the problem without imposing a second order interpretation on it. So that's sort of reassuring we got our same solution back. Now, however, this is I think the second order part of the story has a role here, especially if you want to relate it to the one of the equations on the figure. Is we see that that because of the fact that the damping ratio natural frequency product is equal to 1, this term is a -1. Okay. So and we can jump ahead just because we can see where this formula came from. See the one kind of at first, if without going through the second order discussion, it may look a little strange. We see, in fact, when it at the value equal to a -1, okay, where it turns out k would be 1. That's where essentially we'll see that we have what might be called critical damping, and then as we go above and below, we get under damping, and in this region we could argue we had over damping, critical damping, and then going up and down we had under damping. Let's go back. So, but the point is that where those two poles converge was right there at a -1. And if we go back for the previous page, we would argue that when at the point where k is equal to 1, let's go back here. When k is equal to 1, then omega n is equal to 1. Okay, and then we would say, okay, then we would have the damping ratio here is equal to 1. Let's find that one too here. Okay, k equal to 1, and therefore that term right there is 1, and that's the point where, notice these are equivalent. So that's the point where the part under the radical would vanish, as we talked about before, and both terms converge on that -1, which corresponds to critical damping. Any questions about that? I'm not hearing any questions. Okay. Um, there's a short example which is intended to illustrate, how someone may use the root locus business uh, to put a limit on one of our performance measures. And I'll remind you of this that came out of chapter 5A, which we not too long ago finished off, is that there's these two parameters. One was called the percent overshoot, and the damping ratio. Okay, when you're underdamped, right? When you're underdamped, that damping ratio is getting smaller, and basically you're moving up that axis, and K is getting bigger. So it's the idea being that once you exceed K bigger than 1, remember, and that's where you're going up and down that vertical leg of the root locus, then the damping ratio will be less than 1, okay, and it continues to become lower and lower as the K becomes bigger, okay. So we can see that the percent overshoot, which is no surprise, as the damping factor gets smaller, the percent overshoot goes up. That may be a little undesirable for some applications. Or you may be paying attention to another performance parameter called the settling time. And again, we see that as the damping ratio gets smaller, that settling time gets bigger. Say so, and we know that these two trends here are consistent with making the K too big, right? Because that relationship between the root locus parameter and the damping ratio. Sometimes called the damping factor. Okay, so there's this example, and I think it's the next page. Oh, okay. We talked about this page a little bit, but we didn't finish it. Okay, so from the viewpoint of a second order treatment, we've already established where that formula comes from. We see, in fact, what's going to happen is when the K is between 0 and 1, the roots to the characteristic equation move from the right towards the -1, from the left towards the -1. At K equal to 1, then that more or less converge on that point, and then as you make K bigger than 1, then they go off. The roots go above and below that point on the complex plane, and they're complex. Okay, that's increasing K. And we can even attach now a certain significance to the to the K connection to properties we may have already heard about. We would have heard about back in chapter 2. Certainly, when the K is less than 1, both of our roots are real, and that's for overdamped. K is equal to 1, you're critically damped, and K less than 1. Sorry, okay, this should have been. Let's see, this should have been. These got reversed. I mean, they should have been. That's why I like a document camera. That should be. You might make a note. I'll make a note in my notes to fix that. That's on page 8. That should be. They got cut and paste on that, so that should be, I believe, K greater than 1 and damping ratio less than 1. Okay, so just you may want to make a note that the inequalities need to be reversed on that third leg there on the bottom, but otherwise I think it's okay. And I'll fix it in the notes later. Probably not the best time to do it now. Okay. No, let's see. Well, maybe I can do it now. Hold on a minute. Oops. Oh, let's see. No, to fix it now, I got to get completely out of this and then edit it and then go back in. So I'll fix it later. Okay. Now we may see that there's some interesting language used on this figure, which is not intended to be confusing, but maybe worth pointing out. The boxes here are really poles, okay? Just like, you know, we normally use X's for poles, but for this particular figure, he's only used the X's for poles for the case for K equal to 0. So as soon as K became bigger than 0, he stopped using the X's and started using boxes. Well, that was his choice, and I'm not sure I have a problem with it. I just want to point out to you that normally wherever poles are at, we use X's. So now he is referred to. He's referred to the poles of the open loop system. Okay, well, how do we get the poles of the open loop system? Well, that's by opening up the loop, and we could argue if we opened up the feedback loop, break the disconnection, then the feed forward path is the only connections that exist between the input side and the output side. And so almost by inspection, here's your transfer function under those conditions. We see that yes, the correct poles would in fact be S at the origin and at -2. Okay, now as soon as the K becomes bigger than he wants to include the closed loop. Okay, the closed loop, he's using the box. Okay, that's fine. I mean, I guess normally in root locus diagrams, you use an X wherever there's a pole, period. But I guess this is his choice for this figure. Any questions about that? Okay. So hopefully argued now one of the subtle points, I guess, just so I don't just completely skip over it, one of the subtle points that I thought would be a good question is in fact, well, you could argue that with this block diagram, the condition for the poles, the ones at 0 and 2, -2, only really do occur for K equal to 0, as we saw before. And then as soon as we increase K, that would be, then we saw the poles move. And this would be, I would argue, this is one of the best rationales for recognizing the alternative block diagram model, which has the same root locus, because we can see that if that were the case, let's go down to the bottom and go up. Let me see, I think this is one right here. You can see it, I mean, mine's blocked a little bit there, but anyway, if you look at this one, you set K equal to 0, it takes the feedback path out. And yes, the poles identified are the correct ones, and it does, and you still get a signal through. So I would argue that you could see a little bit of advantage for that alternate block diagram representation that has the same characteristic equation and therefore the same root locus. And okay, so just to remind, notice you see the natural frequency showing up here and here, and of course that's that's consistent with our chapter 2 discussion for second order systems. Right, measured with respect to the origin, which is right, I believe right there. All right, so I think I got an example on the next page. Right, here's an example. Okay, so to avoid excessive overshoot, we're told to keep the angle theta for the underdamped second order systems less than 45 degrees. And of course, I'll remind you the fact that we saw that as the K went to became bigger and bigger, greater than 1, the poles, root locus poles, moved up, and you could say on the positive side and the negative side, away from the -1. Okay, so one would argue that as that k became bigger and bigger, that angle just opened up more and more. But also we know that that corresponds because higher values of k would correspond to smaller damping ratios, damping factor. So from that rule right there at the bottom. So you could say, well, let's say our intention is to put a limit on the how high that angle can be, with the intent of knowing that puts a limit on the percent overshoot, for example. So we're arbitrarily, we could have taken 30 degrees and been the same, pretty much the same steps. The problem, let's take 45 degrees, just to take a number. And so we want to, the question is, we want to find the highest root locus parameter k that would be consistent with keeping the the poles in a location such that that angle theta is less than or equal to 45 degrees. So the figure here is intended to kind of lead us along a little bit. I mean, you imagine that you can put dashed lines here for where those poles exist, essentially horizontally, and argue, well, if they went outside of those dashed lines, your system is exhibiting too much overshoot for the purpose of design, you know, and so maybe that's your criteria. So we want to find the highest k that we can have and still meet that design guideline of staying let's say less than 45 degrees. So let's see. Since 45 degrees is pi over 4, we know that. We can, in order to get that k, one of the ideas here would be we would recognize that there's a connection between k and the damping factor. So all we need to do is use our connection between the angle theta and the damping factor, and then we've got our connection between the damping factor and k. So there's kind of a thread of logic there. So we can get realizing our famous formula from chapter 2 that the damping factor is equal to the cosine of that angle. We could say, well, and as we move up that axis, the damping factor is in fact dropping because less damped, okay, and we're getting more overshoot. So our minimum of that damping factor then is dictated by the cosine of the angle, where the angle is our maximum angle that we can have. I'll let you check the cosine of 45 is, I think, 0.707 approximately. And we can say, well, that's our damping factor. Now we can use our formula from the previous page, which relates the damping factor to the root locus constant, solve for the root locus constant, which in general looks like this, but since we're dealing with the minimum, then that would give us the maximum of the root locus parameter, which is what we want. And since our minimum is 0.707, squaring the damping factor gives 0.5, and then plugging it in would give us the maximum value for the root locus parameters too. So for the most part, so k equal to 0, we had our poles at, what was it, 0 and a -2, k equal to 1, they came together. And then between k equal to 1 to k equal to 2, we met the condition for keeping the overshoot within the bounds of the design. Any questions on that? And everything clear? Anything clear? Anybody hear me?
Yes, we hear you.
Oh, okay, all right. And sometimes I wonder when I don't get a response. All right. Now, it is important for me to point out to you I think, and this is where I'm going to point it out. The method that we came up with the K here is not the typical technique that goes with the root locus methods. Okay, now to do the technique that goes with the root locus methods, which we're now going to demonstrate, I would first like to point out, because it will be helpful on, for this method, to say, well, you know, when K was equal to 2, we knew where the poles were at. Okay, I mean, say we're working backwards here. We knew where the poles were at, and then we got the 2. But anyway, we know that those poles are sitting just where you see them. If this is 45 degrees, when K is equal to 2, so you get these 2 different poles on the essentially having a real part of a -1 and then having an imaginary part as we see it. Now, to streamline the method for finding the K, we can in fact from a root locus method, having knowledge of where those poles are at for the specific K we are interested in is sufficient. So, and what I mean by that is, let's just say I make the observation, which would be in agreement with the picture, and then our K value being 2, that we would say, okay, for the condition we're interested in, the poles existed at a -1 plus or minus J. Now you have to ask yourself, well, this is a right triangle. And is there any other properties of the right triangle here that I could argue? You can have a lot of right triangles, but this one has one property that may stick out. What is it? It's a name often attached to certain triangles have this property. What is it?
Isosceles.
Isosceles, right. Basically, the 2 sides are the same, right? Because we know that's 45 degrees. Okay, that means that if you basically the cosine of 45 is the same as the sine of 45, and therefore that both sides of here are going to, since this is 1, this has to be 1. Therefore, the roots associated with this picture when theta is 45 degrees are the following. Now let's just say I happen to know that's the condition in which I want to find the K. So the method that is often used with root locus is more or less consistent with that philosophy. And all we have to use is, remember the one I said, one of those 2 rules that pops out immediately that seems to be used over and over again was the one based on the K times G equal to a -1. And in this case, we're not interested in the angle condition so much, but we are interested in this result, the magnitude of K times G equal to 1. Now, it may not immediately jump out at you, but after today, I'm hoping it will. And that is, well, we can say, because we know that the root locus parameters are limited to be real and positive, meaning that we just go ahead and pull that K through, and it really doesn't change this expression. So we can then pull it through, okay, and that becomes K times the magnitude of G of S equal to 1. And that allows us to solve for the K from this formula, 1 over the magnitude of G of S. I think you can start to see where we're going. All I need to do then is, and it wouldn't matter which one I take, when we realize there's actually 2 different poles that in principle I could substitute in for S, and I should get the same K, and I'll let you check the other one. We're only going to do the one on the upper half. I contend if you took the pole for the lower half and followed the same steps, you would end up with the same conclusion. Okay, but let's follow it through for the upper half one, and I'll leave the lower half one as sort of a fun exercise for you, which would be a -1 minus J. All right, so so the idea is we're going to plug in for the specific pole where that we know where that K occurred. We're going to plug in with this G of S, and the contention is you get the right you get the right root locus constant that you need. So I'm going to plug in, and I'm here, notice I'm taking the G of S, just like we would have had it before. That was our G of S before. Plug in the S equal to a -1 plus J. And again, I contend you could do it with the other one, and if you follow the steps, you're going to get the same answer. But if we do that, check my arithmetic here, you get a -1 plus J for the first S, and of course a -1 plus J for the second one, but then you can simplify it because a -1 plus 2 is a +1. So then you get the form we see here. Now we could say, okay, so let's see, we're going to take the magnitude of that. Now, one little trick that I believe, according to my slide here, that you can do is one of the properties of, I have to say in words, even though I have an equation for it. One of the properties of words when it comes to complex numbers is the magnitude of the ratio is the what? It's one of those famous jingles that sometimes is useful to remember. If you have ratio of two complex numbers and you take the magnitude of that ratio, the magnitude of the ratio is the anybody hear the question?
Just don't know the answer.
Just don't know the answer. Okay. This is okay. Well, I'll tell you how to show it. Unfortunately, this is where document cameras are superior, in my opinion. Anyway, I'll just have to mention a few words how you can show it. If you have ratio of two complex numbers, all you have to do is represent both top and bottom in polar form. Okay, and then simplify it, right? And then you get the ratio of the magnitudes times some exponential, which represents the phase, but that part has to be, that also, you have to be included that in the magnitudes, but the magnitude in that case, you can just pull out the part that's real and positive, which would be just the magnitude, and then you take the magnitude of the complex exponential, which is 1. So in brief, it comes down to the little jingle I'm looking for. I thought maybe so you've heard before that when it comes to complex numbers, the magnitude of the ratio is the ratio of the magnitudes. And what that really means is, well, 1 is a number in the complex plane, just like any old complex number is, just a specific case of the complex plane. So you can think of 1 as a complex number also, and the magnitude of 1 is 1. In the case of real numbers, of course, the magnitude is like the absolute value. So, and then in the bottom, all we have to do is evaluate the magnitude at the bottom. Okay. So, and then let's just say, use your imagination here. If I have the product of two complex numbers, and I want the magnitude of the product of two complex numbers, I could argue that the magnitude of the product is the, I was thinking, if you thought about the other one, you would understand this one. The magnitude of the product
of the magnitude.
Yeah, that's right. It's the product of the magnitudes. So therefore, you can split this up into two pieces. I mean, you could work it all out, and I mean, there may be half a dozen ways to do this. I'm just trying to show you the fastest. And so, if you essentially use that rule about the magnitude of the product is product of magnitudes, then you just simply have to worry about working out the magnitude of the -1 plus j and the 1 plus j separately. You don't have to, be careful multiplying this thing out. All you have to do is just look at this one, and you realize that, well, the magnitude of a -1 plus j is the square root of 2, and the magnitude of 1 plus j is the square root of 2. And then you're pretty much home free. That means square root of 2 times square root of 2 is 2, so you get 1/2. So if we then plug this in to our formula here, noticing that what we did was we took an S that corresponded to the pole for which we were trying to figure out the associated root locus parameter, we actually would have to put in for that K max, remember that's which we're hoping to find is 2. If we put in the 1/2 in the denominator, yes, we get 2. And I just want to point out to you, hopefully you see that the method here is different. And this one is consistent with what we considered a standard root locus method. Any questions on this? Now, you could argue there really is no real required connection here back to second order systems. All you need to know is you say, well, if you tell me an S that exists on the root locus, I know the root locus, let's say, through some other means we'll explain. I know the root locus, and if I can put in one of those S's in that root locus, it will give me the associated K that led to that point in the root locus. And that's the big idea here. And you can say, well, the second order discussion was not required for this page. Any questions? I mean, if you don't stop me, I'll just keep going. So, I mean, I'm not saying it's a bad thing because we do have some agenda, but so is everything clear so far? Really?
Is there a particular part of this that we're calling the root locus, or is this just we're just calling this whole thing the root locus method or something?
See, I'm not okay. So, what is your question? Okay. I'm going to interpret this question, but I may be guessing. Root locus is, let's say, what you end up with, right? Okay, so we saw that you can generate a root locus using just bare bones mathematics. And this is fine for cases that are particularly simple. But what this chapter is about is not so much just the root locus itself, but the specific root locus techniques that manages to allow you to predict the root locus without that doing it either numerically with a computer or in simple cases you can solve it like we just proved. So there's if the heart of your question is this all about the root locus, I would say it's about the root locus techniques. Now, may have not hit on your question, but if I didn't, you can ask it again.
Is a root locus supposed to is it defining a range?
It is defining a set of points that will exist in the complex plane, which represents the roots to the characteristic equation, which we know are the poles of the transfer function. And we know define things like whether the system is stable or unstable.
Okay.
So we've already talked about one technique that is built into the root locus techniques, and I want to talk about another one now. And we're going to use our original example kind of as a prototype for identifying some of these techniques and clarifying them. So let's take a look at our root locus that we came up with for this problem right here. And you notice I think I pretty much the figure says 1,000 words. We know that when k was equal to 0, we had the pole at 0 and a minus. Oops, 0 and a -2, and then basically as k progressed, reached 1, they collided. I love the language of this subject. They collided and then went off into off at 90 degrees from each, essentially relative to the real axis, up and down. And so that this picture is intended to represent that. Now, we found out in doing this that the only places on the real axis where the root locus existed happen to be between, as trivial as that observation seems to be now, is between 0 and a -2. Now, if you look at the real axis, when all is said and done, we didn't have any of those points to the right of 0. We didn't have any root locus points to the right of 0. We didn't have any root locus points to the left of a -2. Okay, and then everything between these two poles, 0 and a -2, was filled with root locus points. Now, it turns out, kind of as a bootstrap to getting the full root locus, we'll find out this is one of the early steps you take, is to establish where on the root locus root locus, where on the real axis the root locus will exist. Now, the method is that we're going to be using is consistent with the following observation. Imagine that you started counting here the poles. We'll find out that it's actually simpler. It's even when you got zeros in the transfer function, there's a version of this which is pretty much the same. But imagine, since we know we had these two essentially poles, right? Okay, that we see here, that we could argue existed under the k equal to 0 condition. We would argue by looking back here, and we could say, well, we know that they're here. There's what was one at s equal to 0 and one at s equal to a -2. Now, according to this technique, if you started counting the roots, and we could say refer to as the roots of in this case the roots of the characteristic equation, you would number, let's say if you started from the right going to the left, you would number the first one on the real axis as number 1 and the second one as number 2. Okay. Now, I put some of my own personal notes I generated having covered this subject before on Canvas, but we're not going to, it's in the reference section. I noticed can be proven. And so I'm not going to, as opposed to I'm going to overlook the fact that, sometimes understanding where things come from do really help apply it. I'm fairly convinced we can apply these methods even if you don't go through the proof, but if you want to, I put some notes in. But I'm going to explain how it works. So the idea would be that we come down here and we would start numbering from the right going to left, and that would be number 1 and this would be number 2. And the rule is, and this is one of the techniques, the rule is we'll find that the root locus will exist for that part of the real axis to the left. That's important. To the left of the odd number, and I could call it a root here. We'll see that that's really the more correct way to put it, even though we know there are also the poles of the characteristic equation. To the left of the odd numbered roots. So in brief, we'd say, well, that rule is consistent with what we've seen because it's to the left of the number 1 root, yes, but it's not to the left of the number 2 root. We never had any root locus there. So in a way, we're using this as a bootstrap to demonstrate the validity of this rule in its simplest term. All right. Now it turns out that that kind of reasoning is pretty much instrumental to getting that root locus going. Okay. Now here's another example. And again, I'm in lieu of a proof, we're going to kind of just do a couple examples. But if you're interested, I did put my own notes on Canvas. So but I'm not going to take time out to go through it because I usually don't ask students to prove things on exams. Okay, so let's take our G of S. Here we have 2 poles and 1 0. So the 0 is at a -2, a pole at s equal to 0, and another pole at s equal to -4. If you have any question about that, speak up, because that's sort of like what we have to kick off this discussion. Now, according to the rule, root locus, and you start, and since these are, one comment. I put it at the bottom here.
We're actually past time.
Oh, okay. That's what happens when I start talking about root locus. All right. Then we'll pick this up on Monday. On Monday. Thank you for telling me that. All right. Oh, let's see. Just one quick comment. I think we at least need to warn you. Unless I'm mistaken, I would ask you to look at the get ready for opening the floor to questions on the homeworks. Would be 6. I think it's from chapter 5 would be 6A and 6B, which the solutions are posted. So you might want to look at those over the weekend, because we probably want to do that. Anyway, that's all I have to say on that. Yeah. All right. All right. Thanks. I'll end the meeting here. Let's see how I got this. Okay, end meeting.